Okay, in this lesson, we will talk about arithmetic expression evaluation, specifically using stack data structure and infix and postfix notation to do arithmetic expression evaluation. This is not specific to any programming language, but just the algorithm to do it, right? So an important application of stacks is using it to evaluate expressions like these, which have parentheses and orders of precedence and such. So the approach is to break this into two parts. The first is to convert this notation, which is called an infix notation, into something called a postfix notation. And the second is to do a simple postfix expression processing to get the final answer, right? So let's just talk about what are infix and postfix notation, right? So typically when we write expressions, we write them in infix notation. That means that you have the operator in the middle and the two operands on either side, right? In postfix notation, you have the operator at the end. You have the two operands and followed by the operator. This is called a postfix notation. Now, where does this come from? This is also sometimes known as reverse Polish notation, which is RPN, invented by a Polish mathematician, and hence the name using his nationality, right? It was kind of rediscovered, reinvented in 1960 by Bauer and Dijkstra, and used to reduce computer memory access and the use of stacks and such. In 1970s, HP started using RPN for their calculators, and some of those models still exist today. Right, and there was even, a kind of a movement with its promotional hat, which was called the No Equals movement in the 1980s to boost, used by HP to boost RPN. HP calculators, you ended up entering 2, 5 plus, and instead of having the 2 plus 5 equals 2 to get the answer, you would save the one button push of the equal, right? RPN is also used in some stack-oriented programming languages such as RPL and Forth, right? That are still people tinker with them still to this day, right? So what's the benefit of using reverse Polish notation, right? So let's assume that you have a shopping trip and you buy a couple of items costing 70 and 150 units of currency, and then there's some sales tax of 7.25%. And then you would have this mathematical expression, right? Now, if you put that in a calculator, depending on the calculator, you might get two possibly different answers, right? And that's because of whether it did these, you typed these in and it evaluated these two, added these two first, and then did the multiplication, or it waited till the end and then looked at precedence and such to do it. What postfix gives us is avoids this confusion, and in postfix it is represented in this way, which is the addition is done first and the multiplication is done later, and that precedent is built in to the notation. Parentheses are unnecessary. That's a nice property of postfix, right? So let's talk about what does it mean. I mean, how do you convert something into postfix, right? There is an algorithm for this, an approach to this, and it uses a stack, right? And at the very high level, you would have your expression made up of numbers and operators and parentheses, right? And you would process them. You would read each token one by one and take certain set of steps, right? So at a high level, it is the following, right? If the token is, and if you encounter an integer, you just output it, output the number, right? Now the output represents the postfix notation that you are creating by outputting these things. If the token is an operator, plus, multiply, whatever, divide, you push it onto a stack that you are maintaining, right? If the stack is empty, right? If the stack is not empty, you pop the stack and output whatever's on the stack which are operators of equal or higher precedence, right? And when you're done with that, then you push the operator onto the stack, right? If the token is a left parentheses, you push on the stack. If it's a right parentheses, you pop and output entries till you meet the matching left parentheses, right? And then when you kind of finish, you get to the end, you pop and output everything that is on the stack. That's at a very high level. That is the thing, but to really understand it, you have to actually try it and go through it, right? It'll be very hard in this video to kind of go through an example, but we can go through this a little bit further. So let's imagine this is our expression, and we're maintaining a stack and we're maintaining an output, right? So we first read a 2. Let me move this up. If you first read a 2, and what our algorithm says, if you read a number, just output it, which we did. Then you read a plus. If you read an operator, you push it on the stack. If the stack is empty, stack is indeed empty, so push it on the stack. If you have a left parentheses which we encounter, you put it onto the stack. Now the stack is building up. The stack is going to consist of operators and parentheses, right? Left parentheses. Then you encounter a 4. It's fairly simple. You output it. If you encounter a plus, it's an operator. If the stack is not empty, there is nothing that is equal or higher precedence before the left parentheses, so you just put that onto the stack. You encounter 3, you output it. You encounter you encounter a multiplication, right? And you look for anything that is equal or higher precedence. There is nothing, because plus is lower precedence, right? The order of precedence is plus, minus, multiplication, divide in increasing order, so there is nothing. Now you encounter a 2, you output it. Now here's where it's interesting. You encounter a plus, and there is things of equal and higher precedence, so you would output you pop the first thing, which is a multiplication. You pop the next thing, which is a plus, and then you take this and you push it onto the stack, and on and on it goes till what you end up getting is in the output is the same infix expression in postfix format, right? Okay, so now we got our postfix, right? And so what do you do? How do you get the actual number, the result? This part is fairly easy. You will also need a stack, but this time the stack is of numbers, right? And we'll go through it because this is very simple. The algorithm basically is if you find a number, you push it onto the stack. If you find an operator, you pop the top 2 things onto the stack. Apply the operator and stick the result onto the stack, right? So you find a 2, you put it onto the stack. You find a 4, you put it onto the stack. You find a 3, you put it onto the stack. You find a 2, you put it on the stack. Now you encounter the multiplication operator. You take the top 2 things on the stack, pop them, apply the operator. 3 times 2 gets you 6, and you push that onto the stack. Now you get a plus. You pop the top 2 things, 6 and 4, you apply this and you push that on. You keep on doing this till there's only one number left on the stack, and that is the result. And that is indeed what the above expression evaluates to if you work through this, right? So one thing to note here is when you're dealing with the division, you have to be careful in what order you pop and apply this, because 11 divided by 3 is very different from 3 divided by 11, right? So this is not a commutative operation, right? So this has been a description of arithmetic expression evaluation the algorithm for it using the stack data structure. You'll need a stack of operators to create a postfix notation, and then you'll need a stack of numbers to get the actual result of evaluating the postfix expression. All right, thank you.